Okay, thank you. So, are there any questions? Okay, let me remind you what have we done last week. So we have been talking about Euclid theorem, saying that if you have two natural numbers with GCD D, GCD is the greatest common divisor, means it's the greatest natural number which divides both A and B. So if D is the GCD of AB, then you can find an integral combination, which means that the coefficients are integral, producing this, an integral combination of A and B giving D. So the proof is important here because it's not only proving the existence of such an integral combination, it also gives it explicitly, it gives it an algorithm to find K1 and K2. So what we do, we first refer to A and B as remainders. These are the first remainders. After these ones, they're going to be R1, R2, R3. So every time, we begin with the greatest one, A. Suppose A is bigger than B. Okay, so we divide A by B with remainder R1, and then B by R1 with remainder R2, and etc. until, and this progress must finish because we are getting smaller integers, so it is bounded by 0, by 1. Okay, so the last remainder, which is not 0, will be the GCD. So we have seen an example. Now we want to understand why is it true. So our example was, you gave me, I think, these two numbers. So this is the king, this is the queen. So I divide 22 by 16, I get remainder 6, and then 16 by 6, and then 6 by 4. And once I understand that GCD is 2, then I'm going back to find the coefficients that give me 2, the coefficients of 22 and 16. How do I do that? I write 2, I'm going from down to up. Okay, so 2 is 6 minus 4, and then I have 6 and 4 here. So 4 is lower than 6. So I translate 4 to previous remainders. This is 4. Okay, and then I'm gathering together the coefficients of 6. So you have 1 here and 2 here. So you have 3 times 6. Okay, so now you have 6 and 16. So you translate the 6 because 16 is already the queen. Okay. And finally, we're going to see more examples today. Finally, you find this integral combination. Okay. The first combination of the king is the coefficient of the king is 3, and the one of the queen is minus 4. So this is the integral coefficient, the integral combination that gives you 2. Okay, so this gives you actually 2. So why is it true? So if we are looking at the Euclid algorithm, we want to show that Rk is indeed the GCD. In order to show that, we need to show two things. The first one, that Rk divides both A and B. And the second thing we have to show is that Rk is the maximal that does it. So for the first thing, you can see that Rk from here you can see that Rk divides Rk minus 1. You see, it's a factor. So Rk divides Rk minus 1. So if Rk is in here and here, then it also divides Rk minus 2. And Rk divides also Rk minus 3, and etc. So in this way, you show that Rk divides all remainders, including A and B. The second thing that we want to show, okay, is that if you have another integer that does it, I mean, if you have also t, then necessarily t will be smaller or equal to this Rk. And why is it true? Because if t divides both A and B, so it divides also A minus B Q1. I mean, if t is in here as a factor, is also here, so it is here, but this is R1. So t divides R1, okay? And if t divides R1, then it divides also R2, because it divides B minus R1 Q2, which is R2. So actually, finally, t divides also Rk, and this is what we wanted to show, because this gives you that t is smaller or greater than Rk. And finally, once you have this and this, so actually Rk is the greatest common divisor. Okay, so Rk is the greatest common divisor of A and B. And as we have seen, we can reconstruct the coefficients that gives you, the coefficients of A and B that give you this Rk. Let us see another example.
Can you please repeat why divides A minus B?
Yes, because if Rk, Rk or T?
T, why T?
Because if T divides A and B, so it exists as a factor here and as a factor here, then it exists, and then it exists. I mean, you can take out from here and from here some T.
Yeah.
So it divides also the combination of these both.
Right. Thanks.
Okay. So let us see another example. So we want to compute the GCD of these two numbers and also finds the coefficients, the integral combination that gives you this GCD. Okay, so I'm going to do it a little bit more quickly. So 500, and I'm using a computer. Okay, so it's one. Maybe you can help me. It's 1 time 420 plus. Okay, so I'm not counting on myself. I mean, I'm writing 594 minus
174, right?
yes. Okay, and then I take. So how many times you have 107? Two times, isn't it?
Yeah.
Okay, so it's 2 times, and what is the remainder? 72.
No, so
And then how many times do you have 72 in? You have again 2 times.
Mhm.
And we have 144. Then we have 30. And then I want to tell you that this algorithm, I mean, it's not something only theoretical. I mean, this what we do in a cryptographic, okay? So it's a very strength. It is very strong algorithm. Okay, 72. I mean, when I say strong, I mean that the complexity is not too horrible. Okay, 72 is 2 times 12 and it's accidentally we take 2 here. I mean every time. Okay, so this is 6. And finally, so this is the GCD. Okay, the last one which is not 0. And now I want to construct the integral combination. So I'm saying that 6 is 30 minus 2 times 12. Okay, so I have 13 and 12. So instead of, I mean, 12 is below. So I'm writing instead of 12, I'm writing okay, and now I'm gathering the coefficients of 30. So if we have one here and 4 here. So we have 5 times 30 means 2 times 72. Let us think about it. This is 150 and this is 144, so it's okay, it's 6. Now we have 30 and 72. So the lower one is 30. So instead of 30, I'm writing 174. 5 times. Okay. So we have 174 5 times. And 72, we have minus 10 and 2 here, so it's 12. So I'm opening the little computer here, and I'm checking whether it's still 6. Yes, okay. So we have this remainder and this one. So we go to the 72. Instead of 72, we write 420. Okay, this is 72. So gathering together the coefficient of 174, we have 5 here and more 24 here, so it 29 minus we reach the queen 420 times 12. So I'm checking that again. Okay. So we have, so now we reached the, okay, so instead of 174, we write the king minus which is 594 minus 29. Okay. Am I right? No, it's not minus, it's plus. 29 plus 12 is 41, isn't it? Okay, so the K1 is 29 and the K2 is minus 41. Let me check. Yes. Okay. So this is 6.
So I have a computer science question.
Yes.
Hey, what is the complexity? I assume the worst complexity can be very large.
Oh.
And because we are doing this backtracking, can't we do the computation simultaneously? You know, cache stuff up.
Oh, I don't have an exact answer to give you, but I think the following. I mean, you have a tree here. Okay, so it's the 8 of the tree. This is the complexity. I mean, you go down,
Right.
okay, and then you go up.
Right.
I mean, I don't know. I think it's something like logarithmic.
Yeah.
I'm not sure. I'm not sure, but I will check that.
Cool.
Okay. Definition. Two natural numbers A and B are said to be coprime if the GCD is 1. I mean, the greatest common divisor is just 1. They have no bigger common factor, okay? This is coprime. For example, I don't know what you say. And so this is you have 2 here and 7 here as primes. So let us take, for example, 15. Okay. Okay, because here you have, and here we have different primes. So the theorem says that we have seen in Euclides that if you have two natural numbers with GCD D, then you can produce a combination, an integral combination that gives you D. Now the theorem says that if they are core prime, then it's also in the other direction. We have seen in the Euclid algorithm this direction for a general D. Now it says that if they are core prime, I mean, if you find an integral combination that gives you 1, you can be sure that they are core prime. Okay, it's not true to other D, because if you find, for example, 1, you can multiply both sides by some D, so you have another combination that gives you D, but it's not D here. But if you are able to find a combination that gives you 1, then they are core prime. So what is the proof of this claim? The proof is, so this direction is always true. This is Euclid. The other direction says the following. Given an integral combination such that it gives you 1, okay? So suppose the GCD of M and N is D. Now we want to show that if this holds, then this D is 1. But we know that D divides M by definition. And we also know that D divides N by definition. So it must divide also the integral combination, this one. I mean, any integral combination. Because it lies as a factor in both M and N. But what number can be, can divide 1? Only 1. Okay. Corollary. I don't remember. You have 2L here somewhere, isn't it? 2L.
Yeah. So maybe 2 I will check it.
L or 2R? I don't remember.
Yes.
2R, I think. Yes.
So I think it's 2L.
Two
1 R
what?
and 2L.
2L. Yes, it's more reasonable. Okay. Any two sequence a number must be a coprime. I mean, to any n plus 1 is coprime to n, always. Why? Tell me you why. How can I derive this from this theorem?
Yes. So you can put it in the n out.
I can write n plus 1 minus n. So the coefficient here is -1, and here is 1. That's all. Okay. So another corollary, which is more important, there are infinitely many primes. How do I derive this from here? Assume that you have finitely number prime. Okay? Proof. There is finite set of all primes. And let M be their multiplication. Okay, so it's a big number, but it's a finite number. And then what? But M plus 1 is coprime to M. So in this decomposition, you must have other primes of this one. Okay, so it cannot be. It cannot be a finite set of primes. So, I mean, you are not surprised, isn't it? Okay, but what do we need is, what we need is the following one. Definition. Now, I want to remind you, okay, that we have defined this group to any number n. We have defined the group Zn of reminders of all integral number modulo n. Okay. So you have 0, 1 until -1 together with plus modulo n, okay? So this is an abelian group. It's also a cyclic one. It's being generated by this generator. I mean, every element here is infinitely many numbers, all have the same remainder modulo n. Okay? Now, suppose we want to consider not the operation of plus modulo n, but multiplication modulo n. And we want it to be a group. So of course we have to remove 0 because it's not invertible. I mean, all elements in groups are invertible. But it's not enough to remove the 0. Okay, so suppose we want to consider the operation of multiplication modulo n with elements. These are classes. Okay. For example, Z6 is 0, 1, 3, 5. We don't have this. We don't. Okay. It should have been like this. I mean, this should have been a set. Okay. And all this algebraic structure is in with these brackets. Okay, so suppose we want to consider this thing. Okay, it's not the original one because here is multiplication. So of course 0 is not invertible. But I claim that also 2 is not invertible, and also 3 and 4 are not invertible. I mean, you cannot multiply one of these with something here and give and get to 1, because if this is the operation, then the neutral element will be 1 with respect to multiplication. Okay. In fact, 2 and 3 and 4 are, we call it 0 divisors. What do I mean by 0 divisors? I mean that t multiplied with 3 is 0. 0 divisor is some element which is not 0, and being multiplied with another element which is not 0, you get 0. I mean, this cannot happen in our regular Z, but here it can happen because 6 is 0.
Verify how one
Sorry?
are invertible. I'm
5 is invertible because 5 multiplied with itself,
okay.
1 is 1.
Yeah.
So the only element that are invertible here are 1 and 5. These are invertible. One is the neutral element, and 5 is not the neutral, but it is invertible. By the way, you have this phenomenon also in matrices. I mean, you can have also in matrices A multiply with B, which is 0. Though none of them is 0. You know that. Okay? So I mention it because once you have such elements that are 0 divisors, then you cannot you cannot say that if A multiply B is A multiply C, then B is equal to C, because you cannot how do you say it? It's a them. And you cannot just reduce.
Yeah.
Okay.
Cancel out, I think. No, not sure.
Okay. So if we have AB equal to AC, you cannot deduce that B is equal to C. You cannot. Okay, but going back to our targets, okay, we want to take those that are invertible with respect to multiplication modulo n in general. This is called the Euler group, which is very important in cryptography. Okay, so definition. Okay, the Euler group, the Euler for some n natural is, we write it like this, it's just the invertible elements in Zn, but with multiplication modulo n. And this turned out to be exactly all the numbers between 1 and n. Of course, 0 is not included. I mean, all numbers in between that are coprime to n. For example, here, 1 and 5, they are the only number that are coprime to 6. Why is it true? I mean, why do we have this identification? Okay, proof. Proof of that, of this equality. Why is it true? Because if M and N are coprime, this is equivalent, as we said, that you have an integral combination that gives you 1. And this means that n is invertible modulo n, because this is 0. This is exactly equivalent to m being belonging to un. Okay, because it means that you have a number here that multiplied with n is 1 modulo n. Okay. Sorry, not m, mk1. Okay, so being invertible means that you must be coprime to n. Let us see another example. What is U8? U8 is 1, 3, 5, and 7, together with multiplication modulo 8. And U10 is 1, 3, 7, and 9. Multiplication modulo 10. Now, why did I show you these two examples? First, is it clear how did I construct these examples? I mean, I just took the numbers until 8 that are coprime to 8, and here coprime to 10. So you don't have 5, you don't have 6, you don't have 4.
Yeah, this is.
Now, why did I bring you these two examples? Because at first glance, it seems that these two groups are isomorphic. I mean, that you can find some map, injective and surjective, from one to the other that preserves the operation. But the truth is that they are not isomorphic. We are going to talk about it later, but you can see immediately that one of these is cyclic while the other is not. Okay, for example, here, if we take the generator 3, so 3 square is 9, but 9 is 1, so it cannot be a generator. I want to span all the elements using one generator, so this cannot be a generator. 5 also cannot be a generator, because 5 square is 25 is 1. Again, 7, 49 is 1 square. So this is not cyclic. I mean, you don't have here a generator that spent all. Okay, though being abelian, finite, and everywhere. But here, this is cyclic. This is produced by 3. Why? What are all powers of 3? So 3 of the power of 0 is always the identity. It's 1. 3 is 3. 3 square is 9. And this is what is the no, 3 of 3. So this is 7. So you see, I was able to express all the elements by powers of the same 3. So this is a cyclic group, while this one is not. Okay, but these two are Euler groups. This is Euler group U8 and this is U10. Let us see an exercise, okay, in this thing. Okay, exercise. Find the invertible, the inverse of 90 in U143. How do you find a number? First, is it invertible here? The answer is yes, because 90 is coprime, so it belongs to this group. The one and its inverse, it's a group. But how do I find a number here that multiplied with 90 will be 1 modulo 143? What do you say? How can I find this inverse? Okay, so I'm searching for a number that multiplied with 90 will be 1 modulo 143. So actually, I can use the Euclid algorithm. I mean, to find the integral combination that gives you 1, and by this we will find the inverse of 90. Okay, so we are going to use the Euclid algorithm.
Didn't you know that the 90 and 100 co-prime immediately?
Because 90 is 2,
Right.
5, and 3, isn't it? Here is a 3 square, and 143 is 11 with 13, isn't it? So
Yeah.
they don't have a common prime. Okay, so 143 is 1 time 90 plus 53, and then 90 is 1 time 53. Please stop me if I'm doing something wrong. Okay, so here we have 37, and then uh, 3 is 40, 16, and then 5 and 16. Okay. So now let us explore the coefficients of this king and queen that gives you 1. So 1 is 16 minus 15. Now we have 16 and 5. So it is 16 minus, instead of writing 5, okay, I'm writing 37 minus 2 times 16. So it's actually 16, how many times? Here you have 6 times.
Yeah.
So it's 7,
Minus 5.
7
Yes.
times.
Yeah.
So I'm checking. Okay, now we have 16 and 37. So I'm going to translate the 16 to this thing. Okay, so it's 7 times 53 minus 37. How many times? Here we have minus 7, and here we have minus 3. So minus 10 times, isn't it? Let us check it. Okay, so we have 53 and minus and 37. Okay, so we are going to translate 37. We're going to write 90 means. So this is equal to, here we have 7 times, and here we have another 10 times, so it's 17 minus 10 times 90. So again, I'm checking this. Okay. So instead of writing 53, I'm writing okay. Now you have it 70 times minus how many times you have here? 27. This should be equal to 1. Okay. So what is the inverse of 90? For us, I mean, I remember you. I remind you, it's all multiplication modulo 1, 4, 3. So what is the inverse of 90?
27? No.
What is the inverse of 90? I mean, what is the number which will give you 1 modulo 143? Now you have to be careful not to tell me it's 27. Okay? The number that multiplied with 90 is 1 modulo 143 is minus 27. Or if you want, in this word, okay, it's the same as 116. I just add 1 time 144. So this is the solution. Okay, let us check. We just multiplied 90 with 116 and then remove all multiplications of 143. Okay, so I'm using the computer. Okay, this is which is equivalent if I divide it by, I see that you can remove 73 times. Okay. I mean, the simpler way to just check it is to remove one from here and see that it's being divided by this, because it should be one modulo. So if I take 10,049 and I divide it by 143, yes, okay, so this is one. Okay, so this is the answer. This is the inverse of 90. Is it clear?
Yeah.
Okay. We're gonna see how we're gonna use all these things in the algorithm later. This is very interesting. I mean, this is not just mathematics. I mean, we're gonna use it in technology. Okay.
Sorry.
Yes.
I didn't understand how you took from here.
I didn't hear you well.
I didn't understand that how 116. 116.
Because I don't want to use negative. I mean, these two numbers are representative of the same class, modulo 143. So I add 143 to this. You remain with the same remainder.
Oh, okay, okay.
Okay, this is also an answer, a correct answer, but we usually use some positive representative. Okay. So,
Okay, fine.
Okay. Now this is a claim which is obvious. I mean, if you have A, which is congruent to B modulo N, and you have C, which is congruent to D modulo N, then of course AC will be congruent to BD, and A plus C congruent to B plus D. Why is it true? This is very simple to check it, because here the gap is some multiplication by N. Okay, I mean, okay, so in here is also multiplication by N. So I mean, if A, okay, let us, if A is equal to BQ plus some K1N, and C is some DQ1 to plus K2 n. Then once you multiply AC, then you multiply actually this with this, and everything you have, every time you have n is 0. Okay, so AC, sorry, no Q1 here, no Q. This is the meaning of this. A is, I mean, the gap is some multiplication by n, here again. So AC will be BD modulo n. Because all the other, I mean, if you multiply here this by this, then every time you have n is 0 modulo n. Okay, and here is even more simple. Then you can also deduce that a in the power of n, okay, is congruent to b in the power of n, because it's like doing this thing with itself, and no, not n, m. I mean, it doesn't have to be n. When you multiply a with itself m times, so it's like multiplying b with itself with itself m times. Okay. So actually, what I want to say is that if you have one representative or another one, I mean, it's not, I mean, the calculation does not depend on the choice of the representative in the class. Doesn't depend. I mean, if you have a addition or multiplication, it doesn't depend on the choice of the representative. I mean, AC will be like BD, and A plus C will be B and D, and etc. And also the power. For example, let us see an exercise. Solve the equation and 47x is equal to 55 modulo 2000. Okay, this is an equation. An equation. Okay, so you want to find an x such that multiply with x when you remove all integral multiplication of 2000, you get 55. How do you find this x? So the trick is find some, maybe not x, y, okay, that gives you 1 modulo 2000. And then you have just to multiply this y with 55. I mean, first get to the central station, central bus station. I mean, this is 1. Once you get here to 1, it's not a problem from here to get anywhere. Okay, this is the trick. Okay, so solution. We first solve okay. How do we do it? By Euclid. Okay.
I'm sorry, is it 9 or G? I'm not sure how it.
I think I'm saying that if you find such a y
Y.
gives
Okay.
you 1, then 55 times y will give you 55. I mean, first get to 1. From 1 to 55, it's not a problem. I mean, multiply this solution with 55. Okay, so first we have to solve this. So how many times you have 47? I'm going to use again the calculator. So you have 42 times. And the remainder is 26. Now it is 4, 11, okay, 21, isn't it? Here you have 4, 15, and 17, 17 and 4 is 21, right? Okay. Then 26 is plus 5. 21 is plus 1. Okay. Now we have expected that. I mean, because if you don't have a solution to this, you won't have a solution to this. Okay. So now we are getting back. Okay, so 1 is, okay, so you have 5 here. Instead of 5, I'm writing 5. So it is equal to 21. How many times? 1 time here and plus 4. Okay, let me check that. I mean, oh, no, something is not correct. Not 21, 26. Okay. Okay. Now we have 21 and 26. 21 is lower. So instead of 21, I'm writing 5 times. Which is equal to, so here we have 9 times 26. Okay, I'm checking. Okay. So this is equal to 1 after all. So what is the inverse of 41? 47, what is the inverse? Just a minute. I didn't
Missing
finish.
step, right?
I have, of course, I have to find it modulo 2000s. Okay, so it didn't finish yet. I mean, you have here 47 and 26. So 47 is the queen, so we don't touch it. Instead of 26, I'm writing 2000 minus, okay, and then it is equal. So how many times I have 47? 5 times here, and so 9 multiplied with 42 is okay, plus 5. So the inverse of 47 is this modulo 2000. Okay, because this is 0, so this is the inverse. And once I know that this brings 47 to 1, okay, this is our y, then what will be the x?
55.
Yes. Which is of course now I'm removing 20,000 and I get that is okay. So this is the answer. Okay, because 47, okay, if I multiply with this is 1, but if I multiply this with 55, will be 55. So this is the answer. This is x. Okay, so x is 1065. This is x. This is the solution of the equation. Any questions? Okay. Another exercise. Okay. Find 2 in the power of 1000. Okay. Modulo 7. I mean, this is of course a great number. A very large number, very. But if we divide it by 7, the remainder should be a number between 0 and 6. What is the remainder of this large number, modulo 7? How do we solve this? Okay, so the solution is very simple. Why? We know, okay, we know that 2 in the power of 3, okay, which is 8, is 1 modulo 7. So instead of writing 2 to the power of 1000, which can write 2 in the power of 3 in the power of 333 with another power 2. Now this is 1. So this remains 1 because it doesn't depend on the choice of the representative. So if this is 1, 1 remains 1 modulo 7. So the answer is 2. That's all. Okay. Now in the time left, okay. Have you ever heard about? We're gonna continue this next time, okay? But we want to start it now. It's called the Chinese. No, I think we have a double E here. Remainder theorem, okay, or CRT. I'm not sure I've written correctly Chinese, maybe double S here.
So no double. 1 E. And
This is as you can think, as you can suppose. This is a very old theorem due to a Chai Lu. I don't remember his name, but it has more than 1,500 years. Okay, and this is a very basic tool that we are going to use. It says that let these numbers be a set of coprime natural numbers. What do I mean? I mean each 2 are coprime. Each 2 numbers don't, I mean the GCD is 1. Okay, but of course it doesn't mean that these are primes. I mean, with respect one to each other, they are coprime. Okay, denote their multiplication by M. Okay, so M is actually the multiplication of these MI. So given a set of remainders each AI is a number between 0 and mi minus 1. From 1 to k. You have k remainders here. Okay, as the number of the number here. Okay, so given such a set of remainders, okay, there is a unique solution. So we have two things here to prove. First, the existence of the solution, and then the uniqueness. You have a unique solution X to the system of quantities, which is X is congruent to A1 modulo M1, and X is also congruent to A2 modulo M2 until K. Okay, this is the theorem. What does it say? In other words, it says that tell me, I mean, I want to reveal X. I don't know what X is, but I do know is remainders modulo a set of coprime numbers. So tell me who the remainders are, and I will reveal X. Okay? It's like tell me who your friends are, and I tell you who you are. But here is in numbers. So I don't know X, what is X, but I do know that modulo M1 is A1 and X modulo M2 is A2. I do know these. I know these. Then I can find a unique X that these are its remainder modulo these sets. Okay? So this is very powerful. Okay? And how we are going to do, so we are only going to start the proof and continue next time. But I want to understand that you understand the basic notion of this proof. Okay, the basic idea. Okay, we are going, okay, to find E1 until EK numbers, okay, such that EI modulo MJ is, if I is equal to J, then it is 1. And if I is not equal to J, then it is 0. Okay? So we are going to find such E's. Okay? We're going to find K numbers such that each one of them, if you look at EI modulo MI, it is 1. But EI modulo MJ, it is 0. Okay? pay attention that this construction has nothing to do with these remainders. It just have to do with the numbers m. That's all. So we construct this is, and then we're gonna solve this system. X will be what? Will be
The combination.
yes, exactly. This is beautiful. What? How would you call these numbers in algebra? These
Yeah,
are actually what? I didn't hear you.
the standard basis.
This is the basis. Now, why is it the solution? Because x modulo any other m is 0, because this vanishes, all vanishes, this all 0, and this is 1 modulo m1. So you stay with a1, and the same for the others. So this construction is actually a basis. It doesn't have to do with the choice of the remainders, but once you are given remainders, then you can solve this system. I think this is nice, okay? But what we are going to do next time, we don't have time now. So how do we find this ease?
Sometimes Gram-Schmidt.
We are going to see how to construct them, but it's not very complicated. Okay, we are going to construct this ease. Again, it has nothing to do with the remainders, only with these numbers, and then we find a mechanism to solve any such system. Okay, so tell me who are your remainders, and I'm going to tell you who you are. Okay. So we are going to do it next time. Any questions? Do you like these things? I love it personally, but you know, I'm the teacher, so. But as you told you last time, these things are classical, okay? But so it's classical questions, but we're gonna see more complicated methods that deal with these classical questions. Okay, so thank you very much. See you next week.
Thank you.
Thank you.